The first thing we want to do here is quick divisibility proof. So we want to prove that if A divides B and A divides C, then A divides the sum of B plus C. So let A divide B and A divide C. Always want to start with the let statement. So we've let the first part happen. We want to show that the second part happened. And what does it mean that A divides B? Well, all it means is that B is some multiple of A. So B equals A times M. And that's for this one here. And for A dividing C, that means that C can be written as a multiple of A as well. We want to define what these letters are. And those are just integers. One quick addition to this first line up here, we want to make sure that we say what A, B, and C are as well. So we're just going to call them natural numbers. So that'll be our let statement. All right, so we've let A divide B and A divide C, and then defined what that means. So now we just want to use it. And this is a really quick and simple proof. We want to define what B plus C is based on what we know is true, or what we have let be true. So B plus C then is just A times M plus A times N. Which is equal to just factoring on A times M plus N. So at this point, pretty simple stuff. We're really just substituting in based on the definition of divisibility. But we can kind of take a step back and think about what we're trying to prove. We're trying to prove that A divides B plus C. And what that means is we need to prove that we can write B plus C as some multiple of A. All right, so just using that definition, we want to prove that B plus C is just some multiple of A. And so we're pretty close down here. We've got A times M plus N. We know that M plus N are integers, so we just need to essentially make a statement about what M plus N is. So since M and N are integers, their sum has to be an integer as well. And that's really all we need to know. And now we have A times some integer, and we've just shown that B plus C is some multiple of A, and therefore A divides B plus C. Okay, so the next thing that we want to look at here is there are 4 statements on this page here, and they're all really similar, but I want you to pause the video and just kind of mess around with them, check a few of them. So the first one is 3 to the n minus 1 divisible by 2. Is 4 to the n minus 1 divisible by 3, is 7 to the n minus 1 divisible by 6, and is 9 to the n minus 1 divisible by 8. I want you to pause the video and just check a few, just to make sure that you believe that this actually works. So hopefully you've checked a few of these cases, kind of made sure that they make sense. So what we want to do is we want to prove using math induction that all of these cases actually work. So if I pick a number and I raise it to the n power and then I subtract 1 from that, it's actually always divisible by a number less. And you can see that pattern here. So if I raise 3 to a power and then subtract 1, it's divisible by 1 less than 3. 4 to a power minus 1 is divisible by 1 less than 4, and so on. And so we want to actually show that works for all cases. And there's a kind of I don't know, a cute little trick that you'll see within the proof. So let's go ahead and start. Go ahead and start with this proof. So this is a mathematical induction proof. So we always start with let n equal 1. We want to show that the first case actually works. So we're looking at x to the first minus 1. We want to show that that's divisible by x minus 1. And so what we're really trying to show is that x minus 1 equals, x to the n minus 1 is some multiple of x minus 1. All right, so in this particular case, it's just x minus 1. So we know that x to the first minus 1 is equal to 1 times x minus 1. So that works. The first case works. So next part, we want to assume that it works for the kth term. And what we mean by that is that x to the k minus 1 is divisible by x minus 1, or in other words, it equals some multiple of x minus 1. So I can take x minus 1 and multiply it by some number, and I would get the same exact expression. And again, this is for some integer a. So next step here, we want to let n equal k plus 1. So we're looking at the k plus first term. What that means is that x to the k plus 1 minus 1 equals a times x minus 1. So the right side actually doesn't change. We just need to manipulate this left side and show that it's some multiple of x minus 1. So the first thing that I'm going to do is I'm going to take this x to the k plus 1 and I'm going to break it up into its parts. We know that x to the k plus 1 is just equal to x times x to the k based on our exponent properties minus 1. And this is where that cute little trick comes in that I referred to earlier. So what we're going to do is we're going to take this number right here, whatever that number happens to be, and we're going to rewrite it as x minus 1 plus 1. And so we haven't changed anything, because we subtracted it and added it, and then it's times x to the k minus 1. And then we're going to distribute this x to the k to each of those terms. So when I distribute that, I've got x minus 1 times x to the k plus x to the k minus 1. And if you think about this here, the reason that I did this is I need an x to the k in each one of these terms. And I need an x to the k minus 1 in each one of these terms because I've got this definition, or I've assumed that this works up here, x to the k minus 1. I have to use it somewhere. So you see what I've just created is x to the k minus 1 is right here. Using this little trick, I know that that's divisible by a times x minus 1. And then over here, we've got an x minus 1. So it makes sense that this would be divisible by some multiple. Or not some multiple, but actually divisible by x minus 1. So the last thing that we have to do is we know that from the assumption step that this one works. So we just have to figure out that if this one works, and if it does, why? So let's check this out. So remember, what we're trying to do is to show that this whole thing is divisible by x minus 1. So really all we need to do is to show that this is equal to x minus 1 times some integer. So let's go ahead and use what we know. Remember in the assumption step up here, we said that this thing was equal to some multiple of x minus 1, so that's definitely divisible. So let's go ahead and substitute that in. So we've got x minus 1 times x to the k plus, and we already defined this as a times x minus 1 from the assumption step. So this part definitely works. And then this part over here, we need to figure out if x to the k is some integer. So because x is a natural number, and I don't think we defined that up above, but maybe we should. So we're really just trying to do this for natural numbers. So no negatives or zeros for your base on that exponent. But because x is a natural number, any power of x is just repeated multiplication. So that's going to be an integer. So since x is a natural number, and any power of x is going to be a natural number. And therefore, since it's a natural number, it is an integer. So x to the k is an integer, and x minus 1 times x to the k will work. We've got an integer times x to the k. Or I'm sorry, an integer times x minus 1, and that's exactly what we're trying to show. So wrap this up. For all natural numbers, n, and natural numbers, x. And then we just repeat what we started with up here. So x to the n minus 1 is divisible by x minus 1.